Hey everyone, and welcome back to AI by AI. Ever feel like AI is just pulling information out of thin air? Today we're diving deep into what's really going on inside these models, from how they remember things to how they understand the world around them.
Exactly. We've got a packed show today. First, we're cracking open a new way to give transformers better memories, like adding extra RAM to your computer, but for AI. Then we'll explore how to make language models that understand the shape of language itself. Think of it like teaching AI to appreciate the curves of a sentence.
After that, we're talking about a brand new dataset that's teaching AI to see and understand the world like never before. It's like giving AI a pair of super-powered eyes and a library full of knowledge. And we'll also be looking at how much information you can really cram into an AI's brain before it starts to get overloaded. It's like trying to fit all your clothes into a carry-on bag. What are the limits?
Finally, we're wrapping up with a look at a groundbreaking model that's turning AI into a true action taker, capable of navigating digital interfaces and even controlling robots. It's like giving AI a body and a mission. So buckle up, because we're about to explore the cutting edge of AI.
Okay, let's dive into this paper. You do not fully utilize transformers' representation capacity. The core idea is that standard transformers might be leaving performance on the table because they're not fully leveraging the information available in earlier layers.
Right? Transformers are great at capturing context, but the authors argue that the way they're designed, with each layer only directly accessing the output of the previous layer, can lead to what they call representation collapse. What exactly is that?
Think of it like this. Each layer has to compress all the important information from the entire sequence into a single hidden state. As you go deeper, subtle differences between tokens or features can get lost, making them indistinguishable. It's like trying to squeeze an entire encyclopedia into a single paragraph.
That makes sense. So the paper introduces something called Layer Integrated Memory, or LIME, to tackle this. How does LIME work?
LIME is a clever modification to the attention mechanism. Instead of just looking at the output of the immediately preceding layer, LIME allows the model to access and integrate representations from all earlier layers, including the initial token embeddings. It's like having a memory bank of all the past hidden states.
So it's like the model can go back and consult its notes from earlier layers if it needs to. How does it decide which layers to pay attention to?
That's where the router comes in. LIME uses a learned routing mechanism to blend these multi-layer features. The router essentially learns which layers contain the most relevant information for a given token at a given layer. They explore two types of routers, static and dynamic.
Static and dynamic. What's the difference?
A static router uses the same weights for all tokens in a batch. It's simpler and adds less overhead. A dynamic router, on the other hand, computes a different routing matrix for each token, making it more flexible but also more computationally expensive.
Got it. So dynamic is more adaptable but costs more. What did the experiments show? Did LIME actually improve performance?
Yes, across the board. They tested LIME on various language modeling benchmarks and found that it consistently outperformed standard transformer baselines and other state-of-the-art modifications. Plus, they showed that LIME effectively counters representation collapse, preserving higher entropy in deeper layers and improving the separability of closely related tokens.
Entropy and separability. Those sound like fancy terms. Can you break them down?
Sure. Entropy, in this context, refers to the diversity of the representations. Higher entropy means the representations are more varied and less collapsed. Separability refers to how well you can distinguish between different tokens or features in the representation space. If representations are collapsed, similar tokens will be clustered together, making them hard to tell apart.
Okay, so LIME helps keep the representations diverse and distinguishable. What about those depth-wise circuits they mentioned? What are those?
That's one of the coolest parts. By analyzing the learned routing weights, they found that LIME learns interpretable circuits that capture morphological, lexical, and syntactic patterns at different depths. For example, some circuits might focus on English suffixes, while others focus on intensifiers or subordinating conjunctions. It's like the model is learning specialized pathways for different types of information.
That's fascinating. So Lime isn't just improving performance, it's also making the model more interpretable. It sounds like this could be a promising direction for building deeper and more robust transformers. What are the potential downsides or limitations?
Well, the dynamic router is more computationally expensive than the static router. Also, while Lime adds negligible overhead compared to some other methods, it still introduces some additional parameters and flops. The authors also acknowledge that further research is needed to explore the optimal width-to-depth ratio for Lime models and how sparse the Lime routers can be while still maintaining their representational superiority.
So there's still work to be done, but it sounds like Lime is a significant step forward in addressing the representation collapse problem and unlocking the full potential of transformer architectures. It's all about giving the model a better memory and the ability to selectively retrieve information from its past experiences.
Exactly. By decoupling, the burden of storing all relevant context from the single residual stream opens the door to a range of architectural advances that harness earlier layer features more effectively. It's a really interesting approach. Okay, let's dive into this paper on continuous diffusion models for language modeling. It's titled Continuous Diffusion Model for Language Modeling by Jaeyoung Zhou and Seung-Yu Wang. The core idea revolves around improving how diffusion models handle discrete data, like text.
Right? So, diffusion models have been making waves as an alternative to autoregressive models, which generate text sequentially. Diffusion models, on the other hand, can generate sequences in parallel, potentially leading to faster sampling and more controllable generation. But the paper points out that discrete diffusion models, which work directly on discrete data, don't fully exploit the iterative refinement process that makes diffusion models so powerful in continuous data like images.
Exactly. Think about image generation. You start with noise and gradually refine it into a clear image. Discrete diffusion models, because they're jumping between discrete states like words in a vocabulary, lose some of that refinement signal. It's like trying to sculpt something by randomly swapping out chunks of clay instead of carefully shaping it.
That makes sense. So the authors are trying to bridge the gap between discrete and continuous diffusion models for language. They're proposing a continuous diffusion model that incorporates the geometry of the underlying categorical distribution. What does that even mean?
Okay, let's break that down. Categorical distribution just refers to the probability distribution over a set of discrete categories like the words in our vocabulary. The geometry part is where it gets interesting. Imagine each word in your vocabulary as a point in a high-dimensional space. The relationships between these words, how similar or dissimilar they are, define the shape or geometry of this space. This space is called a statistical manifold.
So instead of treating words as isolated, discrete entities, they're embedding them in a continuous space that captures their relationships. How does that help?
By doing this, they can apply continuous diffusion techniques. They establish a connection between discrete diffusion and continuous flow on this statistical manifold. Basically, they're showing that the transitions between words in a discrete diffusion process can be modeled as a continuous flow in this geometric space.
Okay, I think I'm following. So they're not just randomly jumping between words. They're guiding the process along a smooth path in this manifold, preserving more information during the refinement process.
Precisely. They call their model Riemannian Diffusion Language Model, or RDLM. A key part of their approach is a simulation-free training framework based on something called radial symmetry. This is a clever trick to make training more efficient.
Simulation-free training? That sounds important. Diffusion models often require simulating the diffusion process many times during training, which can be computationally expensive.
Right. Their method avoids this by cleverly approximating the transition distribution, which is the probability of moving from one state to another in the diffusion process. They leverage the geometry of the space to make this approximation, leading to significant speed-ups.
So what are the key components of RDLM?
Well, first, they reparameterize discrete data into continuous parameters on the statistical manifold. This allows them to represent words as continuous points in a geometric space. Second, they use a Riemannian diffusion mixture framework to construct a generative process on a hypersphere, which is a specific type of manifold. Third, they introduce this simulation-free training scheme based on radial symmetry to make training more efficient.
And how does RDLM compare to existing models?
In their experiments, RDLM outperforms existing discrete diffusion models on language modeling tasks. It even approaches the performance of autoregressive models, which are still considered state-of-the-art in many cases. They also show that RDLM can be applied to other modalities like image modeling and biological sequence design, achieving impressive results.
That's pretty significant. So this continuous diffusion approach seems to offer a real advantage over traditional discrete diffusion models for language. What about some of the specific techniques they use, like dimension splitting?
Yes, dimension splitting. This is a technique they use to address the challenges of high-dimensional vocabularies. When you have a very large vocabulary, the statistical manifold becomes very high-dimensional, which can lead to training difficulties. Dimension splitting is a way to reduce the dimensionality of the manifold, making the model easier to train and improving its performance.
So it's like breaking down a complex problem into smaller, more manageable pieces. What are some of the limitations or future directions for this work?
The authors acknowledge that their experiments were conducted with relatively small models. Scaling up the model size could unlock even greater potential, particularly in areas like reasoning and planning. They also suggest exploring controllable text generation using guidance methods from continuous diffusion models. Another interesting direction is developing an autoregressive-like diffusion language model by controlling the noise schedule. Finally, they highlight the potential for applying RDLM to other modalities beyond language, such as graph generation and molecule synthesis.
Overall, it sounds like a really promising approach. By bridging the gap between discrete and continuous diffusion models, RDLM offers a new way to think about language generation and opens up some exciting possibilities for future research.
All right, let's dive into this paper on RealSyn, an effective and scalable multimodal interleaved document transformation paradigm. Sounds like a mouthful, right? But the core idea is pretty cool. How can we better train AI models to understand both images and text together?
Exactly. We're talking about vision language representation learning. Think of models like CLIP, which are pre-trained on tons of image-text pairs. They're great at things like zero-shot recognition, meaning they can identify objects in images they've never explicitly been trained on. But the problem is, getting enough paired image-text data is tough.
That's where RealSyn comes in. The authors are tackling this issue of unpaired data, specifically multimodal interleaved documents. Imagine a web page with images and text scattered around, but no clear connection between each image and a specific caption. That's the kind of data they're trying to wrangle.
So how do they do it? First, they've got this real-world data extraction pipeline. They start with a massive dataset called Obelix, which is full of these interleaved documents. They pull out all the images and sentences, ending up with hundreds of millions of each.
But not all data is good data, right? So they filter it. They get rid of low-quality images, anything too small or with a weird aspect ratio. Then they use a CLIP model to find and remove images that are basically duplicates, either visually or semantically.
Smart move. They do the same with the sentences, too. They toss out anything with emojis or URLs, sentences that are too short or too long. They even use something called information entropy to get rid of sentences that don't really say much, and perplexity scores using GPT-2 to filter out sentences that are too difficult or ambiguous.
Okay, so they've got a pile of high-quality images and sentences. Now comes the tricky part, connecting them. They use a hierarchical retrieval method. Basically, they cluster the sentences based on their meaning, then find the cluster that's most relevant to each image. This lets them efficiently associate each image with multiple semantically related texts.
And to make things even better, they add an image semantic augmented generation module. They use a model called OFA to generate a short caption for each image, and another model called RAM++ to extract object detection tags. basically labels for what's in the image. Then they use ChatGPT-4 Turbo to combine the retrieved realistic texts with these captions and tags to create synthetic text.
So they're not just relying on real-world captions, which might be noisy or incomplete. They're augmenting them with AI-generated text that's tailored to the image. It's like giving the model a more complete and accurate description of what it's seeing.
Exactly. And finally, they use a semantic balance sampling strategy. This is all about making sure the dataset is diverse and doesn't overrepresent certain concepts. They cluster the image embeddings and sample more from the smaller clusters, helping the model learn those long-tail concepts that might otherwise get ignored.
So after all that, they end up with RealSyn, a dataset that combines realistic and synthetic texts available in different sizes, 15M, 30M, and 100M, and the results are impressive. Models pre-trained on RealSyn outperform those trained on other datasets in various downstream tasks like image classification and retrieval.
Yeah, the paper shows significant improvements in both linear probing and zero-shot transfer. Linear probing is where you freeze the pre-trained model and train a simple classifier on top of it to see how well the model's representations capture the relevant information. Zero-shot transfer is where you directly apply the pre-trained model to a new task without any further training.
And they also tested the model's robustness, which is how well they perform on images that are different from the training data. Things like adversarial examples or images with different styles. Again, RealSyn-trained models came out on top.
It's not all perfect, though. The authors note that RealSyn sometimes struggles with specific concepts like cars or flowers because those concepts are underrepresented in the dataset. It highlights the importance of data distribution and making sure you have enough examples of everything you want the model to learn.
Definitely. But overall, RealSyn seems like a really promising approach to leveraging unpaired data for vision language learning. The combination of real-world extraction, hierarchical retrieval, semantic augmentation, and balanced sampling is a powerful recipe for creating high-quality training data.
And the fact that they're releasing the dataset and pre-trained model weights is a huge win for the research community. It'll be exciting to see how others build on this work and explore the potential of RealSyn for various applications.
All right, let's dive into this fascinating paper, cramming 1568 tokens into a single vector and back again, exploring the limits of embedding space capacity. It's all about how much information we can squeeze into a language model's input embeddings.
Sounds intriguing. So the basic idea is that current language models, even massive ones, might not be fully utilizing the potential of their input embeddings. Like, they're leaving a lot of information capacity on the table?
Exactly. Think about it. A large language model uses these high-dimensional vectors called embeddings to represent individual words or tokens. But even with relatively small vectors and 16-bit precision, the theoretical information capacity is way higher than what's currently being used. They're talking about a potential lossless compression ratio far exceeding what we're seeing now.
Okay, so lossless compression means we can compress the text and then perfectly reconstruct it, right? No information is lost in the process. And they're saying current methods are only achieving compression ratios of around x10, but theoretically it could be much higher?
Precisely. This paper explores the limits by using a per-sample optimization procedure instead of relying on a fixed encoder model. And guess what? They found vectors with compression ratios up to 1500. That's 2 orders of magnitude better than existing solutions.
Whoa, x1500. That's a huge jump. So how are they achieving this? What's this per-sample optimization all about?
Instead of using a pre-trained model to encode the text into a vector, they optimize the vector directly for each specific text sequence. They freeze the language model and train a special memory vector to encode the entire text. It's like giving each text its own custom-fitted compression algorithm.
Ah, I see. So they're not trying to build a general-purpose compressor. They're tailoring the compression to each individual input. That makes sense. But what determines the limits of this compression? Is it just the length of the text?
That's the interesting part. They found that the compression limits aren't really determined by the length of the input sequence itself, but rather by the amount of uncertainty that needs to be reduced. They measure this uncertainty using cross-entropy.
Okay, cross-entropy. Can you break that down for us? I know it's a common term in machine learning, but a quick refresher would be great.
Sure thing. Cross-entropy in this context is basically a measure of how surprised the language model is by the text. It quantifies the average number of bits needed to encode the sequence, given the model's predictions. Higher cross-entropy means more uncertainty, more surprise, and therefore more information to encode.
Got it. So if the language model can easily predict the text, the cross-entropy will be low and it'll be easier to compress. But if the text is random or unpredictable, the cross-entropy will be high and it'll be harder to compress. Makes sense.
Exactly. And their experiments show that this relationship holds true even for random sequences of words, not just natural language. This suggests that the memory vector is acting as a kind of episodic memory, storing sequence-specific information regardless of whether the model understands the language.
That's a key takeaway, I think. It's not just about the model's pre-existing knowledge. It's about the capacity of the embedding space itself to store information. So what are the practical implications of this research? Are we going to see X1500 compression in our language models anytime soon?
Well, probably not exactly X1500, because their method involves a lot of per-sample optimization, which is computationally expensive. But it does highlight a significant gap between the theoretical capacity of input embeddings and their practical utilization. This suggests there's a lot of room for improvement in model design.
So better encoding and retrieval of contextual information, more efficient episodic memory, and potentially even more complex reasoning within language models. It all boils down to making better use of that embedding space, right?
Precisely. They also found that the compression capacity scales almost linearly with the number of trainable memory vectors. So adding a few extra vectors can dramatically increase the amount of information you can encode.
That's a great point. It's not just about squeezing more information into a single vector. It's also about using multiple vectors more effectively. It sounds like this research opens up a lot of exciting possibilities for future language model architectures.
Definitely. And it also raises some interesting questions about the structure of the embedding space itself. They found that the optimized vectors for the same text can be quite different, and that the space doesn't form a continuous basin where interpolations between vectors would still yield perfect reconstruction. This suggests that there's still a lot we don't understand about how these embeddings are organized.
Yeah, it sounds like there's a lot more to explore in terms of the geometry and topology of the embedding space. But overall, this paper is a really compelling demonstration of the untapped potential of language model input embeddings. It's definitely something to keep an eye on as the field continues to evolve.
Okay, let's dive into this paper about Magma. It's described as a foundation model for multimodal AI agents. What's really cool is that it's designed to understand and interact with both digital and physical environments.
So, like a robot that can also navigate a website? That's pretty ambitious. What makes Magma different from other AI models?
Exactly. The key is that it extends vision language models, or VL models. It keeps their ability to understand language and visuals, but it adds the ability to plan and act in a visual spatial world. They call it spatial temporal intelligence.
Spatial temporal intelligence? Sounds fancy. What does that actually mean?
Think about it like this. It's not just seeing an object, but understanding where it is in space and how it moves over time. This allows Magma to complete tasks like navigating a user interface or manipulating objects with a robot arm.
Okay, I get it. So how did they train Magma to do all this?
They pre-trained it on a massive amount of data, including images, videos, and even robotics data. And here's where it gets interesting. They labeled actionable visual objects in images using something called set of mark, or SOM, and object movements in videos using trace of mark, or tome.
SOM and TOEM, those are new terms for me. What are they?
SOM is like putting digital markers on clickable buttons in a GUI so the model knows where it can take action. Tome is similar, but for videos. It's like tracing the path of a human hand or a robot arm, so the model learns how actions unfold over time.
Ah, so it's a way of teaching the model what's important in the visual data. Makes sense. And what were the results?
The experiments showed that SOM and TOM work really well together. Magma achieved state-of-the-art results on UI navigation and robotic manipulation tasks, even outperforming models specifically designed for those tasks. Plus, it held its own against other large multimodal models on image and video tasks.
That's impressive. So it's a generalist model that can handle a wide range of tasks. What kind of tasks are we talking about?
They tested it on UI navigation, like figuring out how to book a hotel online. They also tested it on vision language understanding, like answering questions about images and videos. And of course, robotic manipulation, like closing a drawer or stacking blocks.
Okay, so it's got the brains and the brawn. What were the key contributions of this research?
First, Magma itself as the first foundation model with both multimodal understanding and spatial temporal reasoning. Second, the SOM and TOM techniques for enhancing spatial temporal intelligence. Third, a large-scale pre-training dataset with UI, robotics data, and instructional videos, all auto-labeled using SOM and TOM.
Auto-labeled? That sounds like a huge time saver.
Definitely. They trained on about 39 million diverse samples. And finally, they showed that Magma performs really well across a wide range of tasks, even achieving state-of-the-art results on some benchmarks without any fine-tuning.
So it's a plug-and-play AI agent? That's the dream, right?
Well, it's a step in that direction. The paper also mentions related work, like large language models and UI agents in the digital world. But the key difference is that Magma is trying to bridge the gap between the digital and physical worlds.
Right? It's not just about understanding, but also about acting. So how does Magma actually work under the hood?
It takes visual observations and a task description as input and outputs a sequence of tokens. These tokens can be verbal like text or spatial like coordinates for a UI element or movements for a robot arm.
So it's translating everything into a language that the model can understand and then act upon. Clever.
Exactly. They even convert 2D and 3D actions into textual tokens to make it easier for the model to learn. But they noticed that there were conflicts between tasks, so they had to figure out how to mitigate those challenges.
Conflicts like what?
Well, predicting 2D coordinates for UI navigation is different from predicting 3D positions for a robot arm. They have different input and output formats. That's where SOM and TOM come in again as a way to bridge that gap.
So SOM and TOM are not just about labeling data, but also about creating a unified interface for the model to learn from. Got it.
Precisely. They also face the challenge of data scaling. There's not as much vision language action data as there is language or image text data, so they figured out how to leverage unlabeled video data using TOM.
That's smart. Videos are everywhere, so being able to learn from them is a huge advantage.
Definitely. They used point tracking models to extract traces of movement from videos, and then used those traces to train Magma to plan and act.
Okay, so to recap, Magma is a multimodal AI agent that can understand and act in both digital and physical environments. It's trained on a massive dataset using SOM and TOM techniques to bridge the gap between different tasks and data types, and it achieves state-of-the-art results on UI navigation and robotic manipulation tasks.
That's the gist of it. It's a really interesting approach to building general-purpose AI agents. Wow, that was quite the journey through the AI landscape. We covered so much ground, from boosting transformer memory to giving AI a body and a mission.
Absolutely. It's amazing to see how researchers are pushing the boundaries of what's possible. That idea of giving models a better memory by allowing them to access information from all layers, not just the previous one, was a real eye-opener. It's like letting them consult their notes from the entire lecture, not just the last sentence.
And then thinking about language models, understanding the shape of language, not just the words themselves. That continuous diffusion approach, modeling language in a geometric space, is such a clever way to refine text generation.
Definitely. And the work on training AI to see and understand the world like we do by combining real and synthetic data is crucial for building more robust and reliable models. It's all about giving them the right kind of eyes and the right kind of knowledge to make sense of the world.
It's fascinating to consider how much information we can actually cram into an AI's brain before it gets overloaded. That exploration of embedding space capacity really challenged our assumptions about how efficiently we're using these models.
And finally, seeing AI models that can actually act in the world, navigating digital interfaces and controlling robots is just mind-blowing. It feels like we're getting closer to truly intelligent agents that can interact with us and their environment in meaningful ways.
It really does. It's exciting to think about where all this is heading. Each of these advancements, from better memory to action-taking abilities, feels like a building block towards something even bigger.
Agreed. And it's clear that there's still so much to explore. From optimizing model architectures to understanding the geometry of embedding spaces, the possibilities seem endless.
Well, that's all the time we have for today. Thanks for joining us on this deep dive into the world of AI. We hope you found it as fascinating as we did.
We'll be back soon with more cutting-edge research and insights. Until then, keep exploring and keep questioning. The future of AI is being written every day.